comes fresh, irrotational. So in the very first moment, there is no boundary layer formed, nothing. You have an irrotational flow. And we are in the very first moment, there is no circulation formed yet. It's an irrotational flow without circulation. Irrotational flow without circulation, okay? You guys know that very well. Irrotational flow without circulation, well, we know it. Here is my circular cylinder. Here is my flow. This is my what? These are what? These points are what? These are my stagnation points. And the flows just flow around the circular cylinder, pure irrotational that we already studied, right? And we already studied this guy. So if you put it here, this is my first stagnation near the leading edge, second stagnation near the trailing edge, but it's on the upper surface. And you guys know what happened, right? What happened in this case? What happened here? Sharp edge, the flow will rotate around the sharp edge, correct? The flow will rotate. If you have no circulation and the stagnation point at the upper surface, the flow will rotate. And I have a sharp edge. If the flow rotates at the sharp edge, what happened to the velocity at the trailing edge here? Yes, it goes to infinity. So it's very large velocity at the beginning, okay? And the flow rotates. And here is a picture. Not this one. You can see here how the flow rotates around an edge. Okay? But this is later on in time. This is not the very first moment in time. You see here the flow rotates around the edge and the flow velocity is very large. But this is later in time. I'll come to this now. Any question about this, first of all? So this is T0 plus. It's the very first moment. We will analyze what happened afterward until we get to the steady state. Any question about this description? The very first moment. Irrotational flow without circulation, because the circulation is not developed yet. Okay? But then if you accept this and you solve your homework problem, maybe the only educational problem in homework 1, you know this. So without circulation, you have some velocity distribution here. It's not very large. But down there, the flow velocity is very large because it will rotate. It rotates at the edge. Okay? It goes actually to infinite. Ideally, theoretically speaking. Now your homework problem was exactly about this, right? What happened? So if you have a very thin layer here, from which the flow comes from very large velocity to very small velocity. What happened? What happened? You solved the homework problem. You cannot say, I have here 7 homework. What happened? We have two layers like this. This is exactly the picture that we had. Correct? Where is the homework problem? This is the homework problem, right? 2 layers with a discontinuity in the velocity. So what happened? A vorticity will generate because of this discontinuity. And you actually derived an expression for how much vorticity is generating, right? So here, because it's the other way around, we have vorticity is generating in this very small layer. So as a resultant, I have a vortex here, starting vortex and I know exactly how fast it is generating. So this is U upper, U lower. It's simply U, the difference squared in the speed, right? This is what you derived, okay? So at the very beginning, because the flow on the lower surface is much faster than the flow on the upper surface. Why? Because of the asymmetry. If you don't have an angle of attack, if it's a zero angle of attack, then it's symmetric. But because of the asymmetry, then the flow here is much larger than the flow there. Much larger speed at the very first moment. This discontinuity of the speed immediately dictates that there is a generation of circulation by the difference in the speed squared. Okay? So now, later in time, I have my airfoil and I have my contour. My contour, I enlarged it, this contour, C, you remember C? I enlarged C now to account for the same fluid particles. And for a contour C with the same fluid particles, if you start with gamma C equals 0, then what does it mean for gamma C all over the time? For all T. What is gamma C for all T?
0.
It's 0. The law of conservation of circulation, as long as you have the same fluid particles. Okay? So this vortex, which is the starting vortex, which is generating here, because this guy immersion generated due to the discontinuity of velocity, and I know that within this fluid bound I have 0 total gamma. So if this guy is generated, there must be another circulation somewhere. I mean, it has to be around the airfoil because nothing actually happens here. So this is your gamma bound. This is the bound circulation for which we have all this. This is gamma bound, the bound circulation that we know. Okay, so at the beginning, the large in velocities, the difference in velocities is very large. I have very large rate of change or rate of generation of circulation here, but how much this is generated exactly dictates how much this is generated. Okay? They balance each other. Okay, now you have a circulation. You don't have an air-rotational flow without circulation anymore. You have a circulation. Do you remember what does circulation do to your stagnation? My stagnation was here at the beginning. If you add a circulation, what happens to your stagnation? It moves, right? And if it's strong enough, it will go to the trailing edge. In other words, this circulation accelerates the flow on the upper surface and decelerates the flow on the lower surface. So later in time, I have my stagnation point was maybe here. It moved, which decreased the difference. This guy is increased a little bit, and this guy decreased a little bit. There's still some difference, but it's not that much. Okay? Still I'm generating vorticity. So still I have gamma dot is U lower squared minus U upper squared divided by U by 2. This gamma dot is larger or less than before? The gamma dot. Larger or less than before? Gamma dot. Come on, guys. It's less. Why? Because the difference in the speeds is less. Okay? You accelerated the flow on the upper surface and decelerated the flow on the lower surface. So gamma dot decreased. Well, my gamma still increasing. Why? Well, because it's still as long as you have a non-zero gamma dot, yeah, it's decreasing, that's fine, but it's non-zero. So this means what? This time rate of change of your gamma. So you pump again. So your gamma is increasing. It's increasing at a slower rate, that's fine, but it's still increasing. And if my starting voltage is increasing, what happened to my bound? What happened to my bound? It's increasing as well, okay? And your bound is increasing. What happened to the separation point? It moves forward. So this difference is less until what?